Project 1.5, Counting Circuit. This project has 8 different subsections labeled A to H, leading up to the final counting circuit. A counting circuit is a circuit that counts up or down using clock pulses. It uses digital components such as a NAND gate oscillator, decade counter, binary decoders, and a 7-segment display. A counting circuit's main function is to precisely track the count number and show it in an easy-to-read format. Part A, Analog Input. Analog input only requires 3 parts. A momentary PBNO is a type of momentary switch that is normally open, meaning it doesn't conduct electricity until pressed. In a pull-up resistor configuration, the resistor connects the PBNO to power. In a pull-down configuration, the resistor connects the PBNO to ground. The final counting circuit uses a pull-up resistor configuration. Part B, NAND gate oscillator. This circuit consists of 7 additional parts. NAND gate oscillators are oscillator circuits that use NAND gates to create repeating square wave signals. By using feedback loops, it creates oscillations using a clock signal. A clock signal is a regular and repetitive electrical signal that provides a timing reference to the circuit so that components in the circuit operate at precise intervals. In the NAND gate oscillator, RC1 and RC2 are resistor-capacitor networks that control the timing characteristics of the oscillator. RC1 controls the timing of the feedback loop, influencing the stability and duration of each oscillation cycle. RC2 determines the charging and discharging time of the capacitor, regulating the frequency of oscillations. The capacitors store and release electrical energy after hitting a certain threshold, which in this case is 4.5 volts since we are using a 9-volt power source. The resistors determine the rate at which the capacitors charge and discharge, collectively determining the oscillation frequency and waveform characteristics of the circuit. Part C, Decade Counter. This circuit consists of 3 additional parts. A decade counter circuit is a digital circuit that counts from 0 to 9 and visually displays the counting using a series of LED segments. This circuit counts through the numbers 0 to 9, each represented by a corresponding bar on the LED bar graph, showing the counts progression visually. The clock input of the 4017 IC is typically connected to an oscillator or clock signal source, in this case the output of a NAND gate oscillator. Each rising edge of the clock pulse advances the count by 1, activating one output pin at a time to light up the corresponding LED segments in the bar graph display. The count progresses from 0 to 9, then rolls over to 0 until the clock signal stops, and the count remains static until reactivated with the PBNO. Part D, Decimal Counting Binary Up/Down Counter. This circuit consists of 4 additional parts. A 4516 is used in the circuit and operates the same way as a 4510. It counts from 0 to 15 instead of 0 to 9, better representing the LEDs in the circuit. A 4510 is used in the final counting circuit. This circuit is configured as a 4-bit binary counter. This counter can count up and down based on the slide switch. The LEDs display the binary count, which each LED representing 1 bit of the counter's output. As the counter progresses through its count sequence, the LEDs light up to reflect the current binary count, offering a simple visual representation of the counter's state. The 4510 chip receives BCD data via input pins, where it sets the initial count value and sequence's starting point. The chip internally processes the BCD input and increases the count after receiving the clock signals from the NGO, using logic circuits to accurately read and advance the count in BCD format. The chip's output signals collectively show the binary-coded decimal count, with each pin correlating to a distinct bit and making the final count number. Parts E and F, Binary Counting Decimal Decoder, and 7-segment display. This circuit consists of 4 additional parts. This circuit is broken up into 2 subsections but ends up as one circuit, serving as the prototype for the final counting circuit. The 4511 internally processes BCD input data, decoding each signal combination to decide which segments of the 7-segment display should be lit to represent the right number. In the output phase, the 4511 produces signals that correspond to the 7-segment display segments, allowing decimal numbers to be displayed. By carefully activating combinations of segments, the chip organizes the display, showing the correct number. The 7-segment display is used for visualizing numbers, comprising of 7 LEDs arranged in a digit pattern. There are 2 variants, common anode and common cathode, differing in their internal wiring arrangements. A common cathode display connects all cathodes together, while each anode is controlled individually, contrasting with the common anode displays, which are the opposite. Our circuit used the common cathode display. To protect the LEDs and chips, each pin requires a resistor to regulate current, preventing excessive current that could harm parts of the circuit. Part G, a Counting Circuit PCB. We are now moving out of the prototype stages and into the final stages. The PCB requires 6 new components, as well as the chips, resistors, and switches shown on the PCB itself. After soldering on all these components, the PCB is complete, but it needs power to function, and this is done with a case. Part H, a counting circuit PCB case. This is the final stage of this project, and once the PCB is screwed onto the case, the final build is done. This requires 3 additional components. Here is a rundown of how this circuit works now that we have finished all stages. Firstly, the 4011 NAND gate oscillator generates clock pulses at a predetermined frequency, serving as the timing reference for the counting process. The 4017 decade counter receives clock pulses and sequentially cycles through 10 output states. Each output state corresponds to a specific count value, allowing the circuit to increment the count with each clock pulse. The 4510 BCD counter translates the binary count from the 4017 into BCD format. The 4511 decoder processes the BCD input data and generates control signals to light specific segments of the 7-segment display. Each combination of BCD input signals corresponds to a segment of the display, enabling the correct representation of the decimal digits. The 7-segment display shows the count progression by illuminating specific segments of the display due to the signals received from the 4511 decoder. This is Project 1.5 Counting Circuit. Thank you for watching.